Everybody, in this video we're going to talk about an introduction to modeling, and specifically, modeling is a really big term that people use a lot and in very different ways, and so I should really define further what I mean by modeling. And so modeling is what we're going to do in the second half of the course, and specifically what we're going to do is called statistical learning or statistical machine learning. And so we're going to focus on what's called machine learning in the second course. And so I want to introduce the types of questions that you might answer with modeling, machine learning, statistical learning, whatever term that we want to use. Okay, and so the visualizations and the material from this are from a book called ISLR, a very popular book. And we're going to use ISLR as our sort of main textbook in Data Science 2. So if you don't have time, or you don't want to take Data Science 2, but you do want to learn that information, or you want to have an outlet to learn that information, I would suggest ISLR. So what we're going to talk about is first the language of modeling, some motivating examples, and then lastly the mathematical formulation of a model. I promise it's not going to be that scary. Okay. So, the language of modeling, as I said before, very, very popular term, widely used in very different ways, is modeling. And so I'm going to define modeling as the process of developing a mathematical or statistical tool to describe the relationship between a set of variables. Okay. There are a number of different variable types. So what does it mean by these variables? Well, you could have a number of observations. You have observations on people, places, or things, but you take multiple measurements on those people, places, or things. Each measurement is called a variable. There are a couple variable types: the response and the predictors. I'll use response and predictors. Other fields use different language. Response is the outcome, event, or quantity that is being predicted or classified or whatever else you can think of. Okay. And the predictors are the variable that are used to model or predict the response. So I think that the number of hours that you study in a class for that class, it has some association, is associated in some way, has some effect on your grade in the course. My predictor would be how many hours a week do you study for my course. My response is the grade you received in the course out of 100, we'll say. And so I'm looking to see, does there seem to be any relationship between that predictor, number of hours you spent studying for the course, the material, and your grade in the course. Yeah? So, predictor, response. Now, what do you want out of a model? There are a couple different things: interpretation or prediction slash classification. So, interpretation is understanding the relationship between the predictors and the response. I want to know, so we'll go back to my example, hour study, grade in the course. Now, traditionally, you would think your intuition, or the intuition of teachers trying to get you to learn the material, at least, is that the more you study, the better that you're going to do. So I'm interested in, if I fit a line, you would imagine a bunch of points. It would look like a scatter plot, number of hours that you studied per week, and then your final grade out of 100. It would be a scatter plot. Teachers would hope, people who are studying this relationship, that are hoping for more study equals better grades, are hoping that the points go up and to the right. So as the number of hours go up, so does the grade. So the relationship on the graph would go up and to the right. If I fit a line to that data, the slope of the line would be positive, indicating a positive relationship. I'd use things like correlation and so on to describe the relationship. All of that is interpreting the model, trying to describe that. If I were interested in a slightly different question based on the number of hours that you study for a class, what's your grade in the class going to be? Yeah, a slightly different question. That's a prediction question. Can I create a model that when I plug in the number of hours I study for a course on average, I'll get an actual grade back of what it thinks is going to happen? It may not be what actually happens, but I'm trying to predict what's going to happen. Not understand the relationship between the situation. So prediction is predicting the value of the response based on the predictors. We're going to learn a bunch of different models in data science too. There are tons of them out there. Ones that are good at interpretation may not be good at prediction, and ones that are good at prediction may not be good at interpretation. They are often different. And so we need to know and understand what do we want to get out of the analysis, and that is going to influence what type of model that we should use. Okay. So there are a couple different examples of modeling questions, maybe to get you thinking a little bit about where I could actually use my data science skills. Okay, and so one that a lot of people use as a canonical example is trying to determine whether or not an email is spam. So I'm trying to create a bespoke spam filter that I create that is not like, I don't know, it's not Microsoft's spam filter, not some company's sort of stock spam filter that's out there. It's one I built on my own, and is like owned by just me, so on and so forth. And so determining whether or not email is spam, that's really important, especially if you get a lot of emails that you don't want. And so this kind of question is, I guess you want to think about, what's your goal in this model? Do you want to understand what it thinks a spam email looks like? So do I want to understand how it makes its decision, or just that it makes the correct decision? So do I want to determine just whether or not email is spam, or what makes an email a spam email? Two different questions. One's interpretation, one is prediction. So this one, I really don't want to, so for this particular question, how I wrote it, this is a prediction question. I just want to have a filter that does a good job at filtering out spam emails. Yes? So, prediction question. Determining what type of media will contribute most to sales. Okay, so I'm at a company who is, well, selling something, and they promote their product in a number of different ways. Newspaper, possibly, although maybe that's a little bit old. Email, social media, so on and so forth. And I want to determine what type of media will contribute most to sales. That is an interpretation question. So it looks like social media seems to increase sales the most, more than newspaper, more than TV, more than email. Okay, the social media influencers seem to have the largest effect. Okay, so that's an interpretation question there. Okay, and then we have one in the middle, determining how much extra will a house be worth if it has the view of a river. Okay. That's maybe somewhere in the middle. So I want to understand how the view of the river affects how much a house will be worth, but it's also important that it's a not just that it goes up or goes down, but by how much it goes up and goes down, and it's important that I get it right. Okay. So those are three different ones. Now, I want to go over that second one, the advertising data. And this is an example from the ISLR book. And a quick aside is that when we first go through this, so actually I won't do the aside yet, but our output is going to be the sales, okay? And then our inputs are going to be TV, radio, and newspaper. Okay, so we have three inputs, X1, X2, and X3. And so if we look at sales versus each of them separately, okay, these are three separate lines, TV, radio, and newspaper, and you look at, say, the slopes of the lines, I think you would say, well, it looks like TV has the greatest effect on sales. Okay, and there's more to be said than this, but this is just the beginning. Now my aside comes in when I first, so this is one of the first examples, or the first example in the book ISLR. And so when they went through this example, I read it and I understood it. But my takeaway from it is that it seems, do sales companies really do this? Was a thought that I had. It seems kind of fake. And I thought that until I had one of my friends worked for Starkist Tuna in Pittsburgh. And he was talking to me about data scientists, about data science in general, about stats and data analysis. And he was working in sales, but he was taking classes and he was learning about data science. And he was talking to me about this example exactly, and that Starkist Tuna, or he was doing this analysis exactly for Starkist Tuna, and he had to add in one more, which was social media influencers, which one is wild to me that Starkist Tuna is advertising people, is that there are such influencers out there that are just talking about Starkist Tuna, but there are lots of food influencers out there, and so that was just my misconception at the beginning. But he did this exact analysis, and he was showing this analysis to like the CEO of Starkist Tuna in like 3 weeks from when I was talking to him. And so that sort of blew my mind that I was maybe a little, I don't know, snooty in a sense, that this was seemingly too simple, but this is, or it's not real enough, but it's actually very real, and probably really important in a lot of different companies. So anyway, that's my aside. We'll move on here. A separate example is Fisher's iris data. Now, this is a very old data set, a fairly old data set that has a number of good and bad things, but really mostly bad connotations attached to it. But we won't really get into that. I'm using this data to show you an example of classification, but there are other really better ones out there, and so I'm not going to talk about it a lot. But we have Fisher's iris data. There are a number of different types of species of irises. Okay, we're going to think about three of them, or there are three of them in this data set: Iris setosa, versicolor, and virginica. And so, based on measurements of this flower, each of the flowers, they have two things about them, or they have the iris has two things: the petal and the sepal. The sepal is of the wide sort of flowery part at the end, the thing that opens up at the end, and then the petal is from the innermost part to the sepal. Okay, so you measure sepal and petal lengths, and so based on those four measurements, sepal length, sepal width, and petal width, can I take those four measurements and try to classify the iris that I have in my hand as one of the three: setosa, versicolor, or virginica. Okay? So the output is the species, the input's petal and sepal lengths and widths. Okay? And this is not a full picture. This is only a two-dimensional graph, but just looking at sepal length versus sepal width, you actually see that there's some pretty good separation. It looks like setosa is very different from versicolor and virginica. There's some overlap in versicolor and virginica, but setosa is very much different. The sepals are short and wide, whereas the other two sort of mix. They are longer and less wide. Okay, now it turns out if you look at these in like a 4-dimensional shape, that versicolor and virginica also separate themselves, like setosa has done here, which makes it an easier classification problem. Okay. Now, the general language of modeling. Here's the what do I want to say? The mathematical formulation of a model. We have a quantitative response y, and then we've got a set of predictors x. So x is a vector here, but it's many predictors. So you have x1 through xp. So p could be any number. So it could be 3, could be 2, could be 800. We've got a set of predictors, some variables, and then we have one quantitative response. Okay? And this is the mathematical formulation. So I told you before that it's not going to be very crazy. Also, sorry for my dog is angry in the background. It is y is a function of x plus error, plus epsilon. Okay, so y is a function of the predictors plus some randomness. Now, where the hard stuff comes in. Now, this simple formulation encapsulates any model that you can think of. I think generally that's true. So anything up from linear regression, which is very simple, to the large language models that have sort of taken over the discourse recently, ChatGPT, such things, they all are this. Okay. Now, the difference is that F is really simple for linear regression, and F is not simple whatsoever in a large language model, like ChatGPT has, and others, and everyone has one nowadays. Okay, so f of x is called the systematic term or terms. Epsilon is the error term. Okay, and so the goal of statistical learning is to estimate that f. Okay, so whatever function of x, a function can be really simple, it can be really crazy. We want to estimate that function. Now, the thing in the background, I guess, is that you'll never really know. Well, statisticians believe that you'll never really know f. Okay, f is going to be unknown. You don't know the real relationship. So in almost anything, it's very hard to tell if you know the actual relationship between grades, how much you study, and certainly there's more going on to how you do in a course than how much you study. There's lots of external factors. We never will be able to actually model reality in general. A model is an approximation of the truth. Okay? There's a very famous quote that I'll use a lot in data science too. All models are wrong. Some models are useful. It was attributed to George Box, or G.E.P. Box, who was a very famous statistician. I don't know if he actually said that. It is. The jury is out on whether he actually said it or it was just sort of an amalgamation of other things that he said that were similar to this. But he was one of many who had this thought, is that all models are going to be wrong. Some are going to be useful. So you're never going to be able to actually model reality successfully, fully. But if you can do it well enough, it's going to be useful. Okay, so anyway, our goal is going to be estimate f, get close to f, or approximate it enough that we can get useful results. Well, how do we estimate f? So this is going to be our last slide. So don't worry, we're not going on much farther. But how do we estimate f? Well, there's a lot of them, and I present them here in a bunch of dichotomies. And I don't know if that's the best way or not, but there are lots of approaches. There's linear and nonlinear approaches. There are parametric versus non-parametric, supervised versus unsupervised. Some that statistics claims, some that the machine learning community claims, and some that are built for regression, and some that are built for classification. Each of them, their methods out there, all have these characteristics. Okay. The general approach of how we're going to try to do it is pick a method to estimate f. We have to pick one, so we're going to pick one and try to satisfy its assumptions. Okay? So for instance, if I have data that looks like a parabola, probably not a great idea to fit a line to data that looks like a parabola, like a linear line. Okay, so y equals mx plus b. Now y equals mx squared plus b, much better. Okay, but just mx plus b, probably not a great idea. Okay, so pick a method. Let the method learn from a set of data. That's called training. So you give it some data. You say this is the relationship. Learn from it. Okay, so it learns from the training set. Then you have to test the method out. Does it actually seem to do a good job on data that it hasn't seen before? That's called testing. And then you assess the current fit and iterate to try to find an optimal fit. So you do this process again and again and again until you find what you think is the best one. Okay? And so that is, well, modeling in whoever knows how many minutes, 20, 30 minutes. Certainly not enough to talk about modeling because we're going to do it for a whole course, but it's the best we can do in the time that we have.